So hello everyone, it's Alexis and I'll be teaching you about Gay-Lussac's law today. So essentially what Gay-Lussac figured out was that when the volume and mass remain constant of an ideal gas, the temperature and pressure of the ideal gas will directly increase or decrease proportionally. So today we're going to go over how it was found, the relationship between the variables, and real-world implications. So this was how it was found by Joseph Gay-Lussac, of course, and we're going to call him Glussac just so it's easier, and honestly the pronunciation sounds better. So he was a French chemist in around the 1800s. He built off the work of Charles, which was one of the laws of ideal gases, but he did a lot of experiments of his own, and he actually published them. So the way he figured out how this law actually came to be was by flying over 7,000 feet above sea level with hydrogen-filled balloons, which is pretty daring if you think about it. But through these experiments, he was actually able to figure out like the direct measurements of gases and a lot of other aspects as well, such as magnetism, but especially pressure and temperature, which is what led to his establishment of this law. So going back to the law, we see that what we're going to work with here is the idea of an ideal gas. So the aspects of gas being that they are constantly and randomly moving molecules, as seen by this diagram right here. They're going to fill up the space of the container, and as the molecules are moving around, they don't have a specific direction where they're going. You know, they're not meant to be someplace. They just move around based on the force that is exerted on them. So if we go back to the equation and the law, relating it back, the two things that are going to remain constant would be the volume and the mass. So that being that the volume is the space occupied by the gas, and the mass being the number of moles in the situation. And as we know, R always stays the same because it's the gas constant. But the two variables that we are going to work with are the temperature and pressure of the ideal gas. So that basically means that temperature being the kinetic energy of a substance, and pressure being the force that's going to be exerted by these little molecules right here on the walls of the container, they are going to directly increase or decrease because they are on the opposite sides of the equation and they have a direct relationship. Going to the molecular level of the two variables that we are going to actually work with today, what we see here is that there are two experiments being set. Here on the left side, pressure and temperature are about the same, you know, they're moving around, they're hitting the walls, but nothing really intense is happening. But here is where we see that the mixture is actually being heated. As we see, heat or the rise in temperature means that more kinetic energy is being put into these molecules. If the molecules have more kinetic energy, that basically means that they are going to move faster, they're going to hit the walls with more force because they need to exert that energy somehow. So there's a direct relationship right there. The molecules will essentially be more charged and start hitting the sides of the walls more, adding more pressure to the gas. So we see that direct relationship right here. So with the real-world applications of this law, I'm going to actually talk about something that I own at my own house, which is hairspray, and it's the same brand right here. On the actual label, it tells me, warning, flammable, do not use near fire or flame or while smoking. But as you can see, any aerosol cans tend to have a warning similar to this because the reason being they don't want to heat the mixture that is inside. That is, if you heat the mixture that is inside, as shown by my diagram right here, that means that more kinetic energy is going to be put into these molecules, meaning that they will have to move faster, just like the relationship that we just discussed. Moving faster means that it hits the walls of the container faster, and the pressure goes up. Eventually, there's so much pressure that is put into the walls of the container that it's going to erupt because the volume has to go overboard to accommodate for the pressure. And that is why you need to follow directions. First, you need to find an egg that won't fit through the top of your bottle. So that's good. And then take a piece of paper, fold it up so it's easier to put in. I'm going to burn it if my lighter works. There we go. Okay. Sure, it's pretty good.
still burning. And then you're gonna put the egg in.
The reason why this demo actually works is because of a lot of combined gas laws. But the reason why this is Gay-Lussac's law is because of the reason that the pressure outside of the bottle and the pressure inside the bottle. So, as seen by this diagram here, the egg drops into the bottle once the match actually, starts losing its fire. So, as we can see here, when the bottle is actually heated up, this means that the bottle is filled with air molecules and the paper actually heats up the molecules, which, as we saw before, the molecules start moving faster and faster, even though it's the same molecules. As a result, some of this air will actually escape from the bottle. We won't actually see it, but that's the reason why the egg is able to go in. Because the air escapes from the bottle, and then it becomes less heated because the flame goes out. That means that since temperature goes down, pressure will also go down. Therefore, the pressure outside the bottle, the outside pressure, is going to be higher than inside the bottle. Therefore, the pressure, as seen by these arrows right here, from outside the bottle is going to push the egg into the bottle because there is less pressure inside. And that is why when the air cools down, there's much less pressure inside, and then the force exerts on the egg and pushes it into the bottle. Thank you for joining me to learn about Glussac's law today.